Okay, I just want to show you that was the results, which problems we wanted, top 5 problems. So I'm not going to talk about the ones that got voted with a 1 or a 2, but I am going to talk about as many of the rest that I can. Okay, you asked for number 3. This is set up in parametric forms. We have x is t squared and y is cosine t squared. The derivative of y with respect to x when we are in parametric mode is dy dt over dx dt. So I'm simply going to take the derivative of the y part of the function, this is considered the y component, and divide by the derivative of the x component. So the derivative of y with respect to t, I have a chain rule in there, so I'm going to have a 2t, and then the derivative of cosine is negative sine. So I'll get negative 2t times the sine of t squared. And then the derivative of x with respect to t, of course, is 2t. So the 2t on the bottom is going to cancel with the 2t on the top. And I have negative sine of t squared. That's choice B. Number 5 is going to be a partial fraction decomposition question. So that denominator factors, the denominator factors into x plus 2 times x plus 3. We step aside and we break that up. X over x plus 2 times x plus 3 breaks down into a over x plus 2 plus b over x plus 3. If I clear the fraction, I'm going to get x equals a times x plus 3 plus b times x plus 2. I chose to let x equal negative 3 to start with. So if x is negative 3, that zeroes out this term, and I'm left with negative b here. So that means b is 3. Now I'll choose to let x equal negative 2. That zeroes out the term with b in it, so I'll get a. So a is negative 2. Okay, I'm going to go back over here now. This can be written as the integral of the sum of these two fractions. So a was negative 2, so I'm going to write negative 2 over x plus 2 plus positive 3 over x plus 3. Negative 2 natural log of the absolute value of x plus 2 plus 3 times the natural log of the absolute value of x plus 3 plus c. There's subtraction between the logs, so it's going to be the log of the quotient. So it'll be the log of, this one's actually going to be on top. So I'm going to write x plus 3 on the top. And this 3 in front of the natural log is actually a power. And then x plus 2 squared. So that looks like choice A. Number 8, I'm going to break that up into 2 fractions to start with. So I'll have the integral of 1 over the square root of 1 minus x squared dx plus the integral of 2x over the square root of 1 minus x squared dx. And we've done problems like this in the past. We just maybe didn't remember to break it up. This is actually the derivative of inverse sine. So we can go right ahead and take the antiderivative. Inverse sine of x is what we get there. And then plus, this one will take a little bit more work. I'm going to need a u substitution. Notice the quadratic in the denominator and the linear in the numerator. So u equals 1 minus x squared. Du equals negative 2x dx. I just need the 2x dx. I don't need the negative. So negative du is going to replace 2x dx in this integral. So I'm going to get a negative out in front. The 2x dx is gone. And then I have 1 over the square root of u du. I want to look at that as this is u to the 1/2, but it's downstairs. So it's u to the negative half du. And then the antiderivative of that is negative 2u to the 1/2. Okay, so I'm going to bring x back into this problem. And remember, the first part of it had a sign. So the first part of it was inverse sine plus, actually that's negative, 2 times 1 minus x squared to the 1/2. So I'm going to put a square root over that, plus c. So which one looks like that over here? Number 10 was the next one you asked for. This one, you could do a couple of ways. I had success when I started with u substitution. So I let u be the natural log of x, which gave me du equals 1 over x dx. Okay, I'm going to change this starting equation to get x by itself. I'll e both sides. So I'll get x equals e to the u. Now I can make substitutions on this integral. I'm going to leave the limits out of it for a moment. X is being replaced with e to the u. The natural log of x is u from the original u substitution. And dx is going to be x du. Okay, obviously I still have an x in the game. And you know I can replace that one also with e to the u. So there'll be e to the u times e to the u. So I'll have the integral of e to the 2u times u du. Okay, I have a product of two functions again. But this time log is not showing. So I'm going to look at it with integration by parts. And I'm going to set up a tabular integration to do it. So since I'm working with u, I'm not going to label this. But this is the polynomial piece. The u is the polynomial function. So I'm going to put u in the first column. And e to the 2u will be the dv, if you will. So this is the column where you take the derivatives. So I'll get a 1 and then I'll get a 0. And then this is where I take the antiderivatives. So the first one will be 1/2 e to the 2u. And then do it again is 1/4 e to the 2u. And in tabular integration, you want to grab the product of these terms on the diagonal and the product of these terms. But remember, every other term has to be negated because of the formula for integration by parts. So there is my setup in tabular integration. And what that means is my answer is the product of these two, which is 1/2 u times e to the 2u minus 1 times this 1/4, so it's going to be 1/4 e to the 2u. So that's actually the antiderivative plus your c, but this is a definite integral. So eventually I'm going to do a substitution and evaluate. First, I'm going to go back into x form so I can use the original limits. U was natural log of x to begin with. So up here I'll have e to the 2 natural log of x, and then 1/4 e to the 2 natural log of x. Now I'm going to need to look at this e to the, so this e to the 2 natural log of x is this 2 natural log of x is also natural log of x squared. So when you take e to the natural log of anything, then it simplifies down to that anything, which is x squared. So this is 1/2 times the natural log of x times x squared. And then the same thing is true here. E to the 2 natural log of x is the same as x squared. So that's 1/4 x squared. And I'm evaluating from 1 to e squared. Those are the limits on the original integral. So I'm going to substitute e squared in first. Natural log of e squared is just 2. So this is 1/2 times 2 times e to the 4th, because that's e squared squared. Then 1/4 times e squared squared, again, is e to the 4th, minus, now I'm going to substitute a 1 in. So when I put 1 in here, the natural log of 1 is 0. So this term is zeroed out. And then when I put a 1 in here, I'm just going to get a 1/4. So over here, the 1/2 and the 2 multiplied to 1, I have e to the 4th minus 1/4 e to the 4th is 3/4 e to the 4th plus 1/4. And I think that looks like choice D. 11, this is one of our favorites. This is an integral from 4 to infinity. And what you want to do is you want to get this 16 out of here. This is of the form arctan. So I'm going to take out the 1/16, factoring out the 16 off the bottom. Let's push that dx over. And then when I factor that out of the bottom, I'm left with x squared over 16 plus 1. I'm going to put this 1/16 out in front, rewrite the denominator. X squared over 16 is the same as x over 4 quantity squared. This is of the form arctan. Coefficient is 1/16, and this is an improper integral. So I need to multiply 1/16 by the limit, and I'll pick a variable t goes to infinity of 4 to t of this 1 over x over 4 squared plus 1. Okay, so now we're ready to go. We should consider improper integrals with a limit. That's the appropriate approach. So I have 1/16 times the limit as t goes to infinity, and the antiderivative here is arctan, or inverse tangent. Inverse tangent of x over 4, and I need a correction factor because of dividing by 4 inside. This is the chain rule. I need to reverse the chain rule. The x is being divided by 4, so I'm going to multiply by 4 to correct for that, and this is being evaluated from 4 to t. Every time you do this correction factor, you just double check yourself. If you went to take the derivative of inverse tangent, you would get 1 over x squared plus 1, where x plus 4 is your argument. Well, you have to take the derivative of x plus 4, which is 1/4, and I have a 4 out there to cancel with the 1/4. Okay, so now I can evaluate. So I'm still waiting on taking a limit because I need to evaluate. I'm going to substitute in t. Let me bring the 4 out in front also. So this 4 is going to come out here. Let me just put it on top of that one for now. And then I'll get inverse tangent of t over 4 minus inverse tangent of 1. I need to remind you what to do here. Do you remember what to do here? I'd like to use this space since I have it. We need to think about the graph of inverse tangent if you don't know what to do with that. Now, normally when you graph trig functions, you would put the angles on the x-axis and you'd go 1, 2, 3, 4. You'd go numbers on the y-axis, but inverse switches that. So hopefully you remember there's problems with tangent at pi over 2 and negative pi over 2. We have undefined tangent values. So there's going to be horizontal asymptotes for inverse tangent at those values. So the inverse tangent function looks like this. And it's right on your calculator. So if this were on the AP test, this particular function, you could throw it in a graphing calculator quickly to get a look at it. But here's the story. As t approaches infinity, this argument becomes very large. So the input becomes very large. And when the input becomes very large for inverse tangent, notice on the graph that inverse tangent approaches pi over 2. So this value is going to pi over 2 when we take the limit. I'm going to rewrite 4/16 as 1/4. In here, I'm getting pi over 2 minus the inverse tangent of 1 is pi over 4. I hope you remembered that. So this is 1/4 times pi over 4, which is pi over 16. So that's choice A. Number 12, the equation of a tangent line. So I'm going to need a slope here. I have the function y equals sine squared x. So I need a derivative for slope. So dy dx, I've got a power rule first. So I'm going to go 2 times sine x and then multiply by the derivative of sine, which is cosine. By the way, this is the same as sine of 2x. So it would really help you if you remember the derivative of sine squared is sine of 2x, and then your calculations could go quicker. But let's say you don't remember that. I'm going to evaluate for x equals pi over 4. So that means I'm finding 2 times the sine of pi over 4 times the cosine of pi over 4. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. I'm getting 1 for the slope. The other thing I need is an ordered pair. So I'm going to evaluate the function at pi over 4. So that's sine squared of pi over 4. So the ordered pair is pi over 4, 1/2. So the answer is y minus 1/2 equals slope is 1 times x minus pi over 4. And that is choice B. Number 13, the idea here is if one of these sine or cosine has an odd power, you're supposed to pull one out. So it doesn't matter which one because they're both odd in this case. So I'm going to leave sine alone. I'm going to take one of the cosines away. So instead of cosine to the third, I'm going to have a cosine to the first. The other two cosines, I'm going to switch them over to sines. So 1 minus sine squared takes care of 2 of the cosines, and the third cosine is going to sit here next to the dx for me because I'm going to do a u substitution. Let u equal sine so that when you take the derivative, you get du equals cosine x dx, and du will replace this cosine x dx. So I have sine to the 5th is going to be u to the 5th times 1 minus u squared du. And you just have to evaluate this. So I'm going to distribute the u to the 5th. So I'll get u to the 5th minus u to the 7th, and the antiderivative of that is 1/6 u to the 6th minus 1/8 u to the 8th plus c. And so I'll get 1/6 sine to the 6th minus 1/8 sine to the 8th plus c, and that looks like choice B. Did not have a lot of requests for number 15, but somebody asked me about L'Hopital's rule. So I just want to point out that if you try to evaluate this with x equals -8, you would get 0 over 0. You can write 0 over 0. I can write 0 over 0. You just don't want to say that this equals 0 over 0. So you could write 0 over 0 in determinate form. Let them know you're going to use L'Hopital's in some way. And that means you're going to take the derivative of the numerator first, which is 2x plus 5, separate from the bottom. So then you take the derivative of the bottom, you'll get 2x plus 10. Okay, now you can take the limit again. So the limit as x goes to -8. So I'm going to get 2 times -8 plus 5 on top and 2 times -8 plus 10 on the bottom. So that's -16 plus 5 over -16 plus 10, which is -11 over -6, which is 11/6.